So we have established that if I take an angular momentum operator, say J, it has three components, Jx, Jy, and Jz. Then of all the operators that I can make from it, I can also make the total angular momentum operator, J squared, which is of course Jx squared plus Jy squared plus Jz squared. Then we can choose two operators from this set, and traditionally those two operators are chosen to be, say, J squared, well, and Jz. So this set commutes with each other. Of course, we don't have a choice in the first one, but the second one, we could have chosen either Jx or Jy or Jz, but we chose Jz, which is the traditional choice. And now what we are going to do is that we are going to find the eigenvalue spectrum of these operators. Of course, these operators commute. And what that means is that we can find wave functions which are simultaneous eigenfunctions of these operators. So before we do that, let's introduce some non-Hermitian operators called J plus and J minus. So J plus is, say, Jx plus I times Jy, and J minus is Jx minus I times Jy. Now, since Jx, Jy, and Jz are Hermitian, so these are Hermitian, that means that if I take J plus and take its Hermitian conjugate, then I'm going to have Jx. The plus sign will now become minus sign because of the I, and this will, Jy is Hermitian, so it will remain Jy. So we will get J minus. So we see that Hermitian conjugation just switches these two operators. Now, we can show that if I take Jz and compute its commutator with J plus, then of course we can write this as Jz commutator Jx plus I times the commutator of Jz times with Jy. Of course, what is the commutator of Jz and Jx? It is nothing but I times Jy. And what is the commutator of Jz and Jy? Well, it is minus of Jx. It's minus I times Jx. So that means that I can write this as Jx plus I Jy, which is nothing but J plus. So we have established that the commutator of Jz with J plus just gives me, again, J plus. So similarly, one can show that the commutator of Jz with J minus gives us minus of J minus. Okay, so this is an important distinction. And similarly, we can evaluate the commutator of J plus and J minus, and a little bit of algebra shows us that this gives us 2 times Jz. So in other words, what we have done is that we have taken the angular momentum algebra, which was, say, the commutator of Jx and Jy is equal to I times Jz, etc. So there were 3 equations, and we have replaced them with these 3 commutation relationships, which are equivalent. Okay. Now we are going to see what is the information that is contained in this commutation relationship as far as the eigenfunctions are concerned.